Today's lesson 10.8 is on geometric probability. So we're going to start by looking at geometric probability on a line, so for length. Then we're going to look at geometric probability for an area. And then finally we'll do a bunch of example problems of both kinds. Alright, so by the end of the class today, you'll be able to find the probability of an event occurring, and there are two types of events. One is a point selected on a number line within a particular range. What is the probability of that occurring? And then secondly, what's the probability of a point selected in a 2D shape being in a shaded region of that shape? Alright, so what is geometric probability? Well, it ranges from 0, meaning there's no probable chance that it's going to happen, to 1, meaning there is a 100% chance that it will happen. And it's simply the length of the area of the length or area of the event that you want over the total length or area. Let me give you an example what that is here. So first we're going to put in our date in our notes. And the probability is the likelihood that an event will occur. It's written as P, or probability of the event, equals the number of winners, or what you're looking for, over the total number of possibilities. And geometric probability is probability that uses geometric models in which points represent outcomes. So, for example, if I tell you that point S is on this line AD and it's chosen at random, the probability that that random point S is on BC is the ratio of the length BC to the length of AD. So in other words, probability that S is on BC is equal to, again, the what we call number of winners, what we want is the point on BC, versus the total number of possibilities, which that would be the point is on AD. So let's do some examples of that. So if a point is chosen randomly on the line segment below JM, what is the probability of the chosen point being on the line segment JK? And we're going to write as a percentage. Okay, so again, the probability of an event is, since we're doing length, is the event length over the total length. Well, the event length is what we're looking for is JK. The total length is that total length of that segment there, which is JM. So JK is 1 long and JM is 3 long. So the chances that if a random point is going to be on JK out of JM is going to be approximately 1/3 or 33%. Okay, now it's asking us the same question, except what is the possibility that that point randomly is going to be on JL if it's on JM? So once again, it's the same formula. The probability is the event length over the total length. So in this case, that would be JL over JM, which would be 2 over 3, which is approximately equal to 67%. This one is asking us what is the length of KL? What are the chances that the point is on KL if it's on JM, if it's chosen at random? Well, once again, KL is 1, JM is 3, so it'll be approximately 1/3. And then finally, what is the possibility of a point at random being on JM being chosen on KM? Well, that would be KM over JM, which equals 2 over 3, which is equal to exactly is equal to approximately 67%. 66.666, 67%. Alright, so here's an example problem in your notes. Try this problem on your own and see if you can do it. And then we'll do it together. So push pause and then come back. Okay, so once again, the probability that K is on QR is the length of QR, the probability of what I want, or the winners, over the whole thing, ST. So the length of QR is 3. R is 8 and Q is 5. 8 minus 5 is 3. And the length of ST, well, T is 14 and S is 2, so that length, 14 minus 2, is 12. So QR over ST is going to equal 3 over 12, which I've reduced it is 1 over 4, which equals exactly 25%. Alright, if you feel comfortable finding the probability of an event occurring of a random point on a line, then pause here and go to classwork 10.8.1 percentage on the number line, and then come back when you're done. Alright, so we've done the probability of a point being on a line. What about the probability of a point being in a shaded area of a region? So the probability in area. So if I tell you that point S is chosen randomly and it's in region R, the probability that point S is in region N, which is in region R, is the ratio of the area of N to the area of region R. So in other words, the probability that S is in region N is equal to the area of N over the area of R. So let's look at some example problems of that. So if I have this circular dartboard here, and darts are thrown at each of the boards below, a dart hits the board at a random point. Find the probability that a dart will land in the shaded region, and again we're going to show it as a percentage rounded if to the nearest percent if necessary. Okay, well, we want the event area over the total area. Well, we don't know what the area is because we don't know what the radius is of this, but what we know is that the shaded area, or what we want, is 360 minus 120, or 240 of the 360 total degrees. So that would be equal to 2/3, or approximately 67%. If I wanted to, I could just pick an area, I could just pick a radius, call it 1, and do the whole thing out, and you'll see that it's going to equal 67%. Right. Here's another one. Now it's a square dartboard, and a dart is thrown at random. What are the possibilities that it's going to hit one of those shaded regions? Okay, well again, it's the probability is the area of the event, or the event area, so that would be the shaded, of which there are 17 squares, and the total area, of which there are a total of 49 squares. So 17 over 49 is approximately equal to 35%. Alright, and then finally, here's a good problem here. I've got a hexagon inscribed in a circle, and I want to know the shaded region here. So the first thing I'm going to do is find the area of each figure. So I'm going to find the area of the circle, I'm going to find the area of that hexagon, and I'm going to find the shaded region. And so the area of the circle, if the radius is 10, then that is 10 squared pi, or about 314 square centimeters. The area of that hexagon, if I draw a line from R to the midpoint of BC, that will make a 30, 60, 90 triangle, and I can solve this whole thing out, and it's equal to exactly 150 root 3 square centimeters, or about 260 square centimeters if I'm rounding it out. And then finally, if I subtract those two to get the shaded region, 100 pi minus 150 root 3 is equal to about 54 centimeters. So once again, if I look at the event area, which is 54, over the total area, which is 314, I get that that is approximately a 17% chance of the point being in the shaded region. Alright, let's do some example problems in our notes. So you should try these problems on your own. Push pause, try these problems on your own, and then come back and see if you got them right here. Alright, so example problem 2 is saying that a circle is inscribed in a square. Point Q in the square is chosen at random. What is the probability that Q lies in the shaded region? So the probability that Q lies in the shaded region is going to equal that shaded area, which is the whole square, minus the circle, over the whole area, which is that square. Okay, well the square is simply a side squared, so that's 6 squared, 36. The circle, if I look, that side of 6 is equal to the diameter of the circle, and therefore the radius is half of that, 3. So pi r squared would be pi 3 squared, or 9 pi, which is about equal to 28.3. So the square minus the circle over the square is equal to 36 minus 28.3 over 36. That's about equal to 7.7 over 36, which is about equal to 21%. So the chances of a point being chosen at random within that square being in the shaded area is approximately 21%. Let's try problem 3. An archery target that's shown here has 5 colored scoring zones formed by concentric circles. Remember, concentric circles are circles that all have the same center. The target's diameter is 122 centimeters. The radius of the yellow zone is 12.2 centimeters. The width of each of the other zones is also 12.2. If an arrow hits the target at a random point, what is the probability that it will hit the red zone? Alright, so we want to find the probability that the arrow is in red. So that would be equal to the red over the entire target. Okay. Well, to find the red, I have to find the circle of that whole red, which is red and yellow together, and then I'm going to subtract out the yellow, because again that yellow is in the middle of it. So I'm going to find the whole red and yellow together and then subtract out the yellow. Okay, well, if the radius is 12.2 and each one is another 12.2, then the red and yellow is 2 of them. That'd be 24.4 squared times pi is about equal to 595.36 pi. And the area of the yellow is going to be 12.2 squared pi, which is 148.84 pi. So if I subtract those, I get that the red is exactly 446.52 pi. The entire target, it said, had a diameter of 122, so its radius is half of that, or 61. So pi r squared, or r squared pi as I have it written here, is 61 squared pi, which would be 3721 pi. So the area of the red over the area of the target is 446.52 pi over 3721 pi, and that would be about equal to 12%. Alright, so if you feel comfortable in doing these problems of finding a point selected in a 2D figure and finding out the percentage or the chances that that is in a shaded region, then you should do classwork 10.8.2, which is some easier problems, and then 10.8.3, which are some shaded region harder problems.